Hi guys, in the last lecture we started with the cases of transient stability analysis. In first case we saw what happens when we increase stream input of the alternator. We saw how the rotor oscillates about the mean position. There we saw in case of first swing, speed went like this, omega s to omega max to again omega s. In second swing it was omega s to omega min to again omega s. That is, the speed of the shaft will keep on oscillating. Similarly, the delta was keeping on oscillating between the two values, delta naught up to delta 2. Then we saw the case when the fault occurs near to the bus. There also we saw how the rotor angle oscillates and the speed also oscillates. Then we determined critical clearing angle, the maximum angle at which the fault can be cleared. It was cos inverse Pm, that is a mechanical power, by P max delta max minus delta naught plus cos delta max, and TCR, which was equal to under root 2m by Pm delta Cr minus delta naught. Remember here Pm is same as your PS naught, that is the mechanical input or the shaft input. So do not get confused in between these two terms. In this lecture we will consider a more general case of the fault occurrence when the fault occurs in middle of one of the lines. Okay, suppose we have two parallel transmission line or a double circuit line in which the fault occurs at middle of one of the line. Now in this case the reactance of the generator is, let us say, xt double dash. The reactance of first line is x and the other line is also x. So before the fault what will happen is both lines are operating in parallel. So transfer reactance would be xd double dash plus x by 2. So maximum power will be mod E mod V by xd double dash plus x by 2. That is the case before the fault occurrence. Okay, and if we consider mechanical input as PS, it will be equal to P, which is equal to P max 1 sine delta naught. So delta naught will be equal to sine inverse PS by P max 1. So before the fault, machine would be operating at this angle, or the system would be operating at a power angle of delta naught. Now what happens during the fault? During the fault, what we have done is we have represented infinite bus bar or system as a motor. Okay, I am considering the load as a motor. It has an EMF EM and it has a reactance XM double dash. Okay. Now when the transmission line is short circuited from the middle, the reactances will divide like this, x by 2 and x by 2. Now we have to find the transfer reactance between these two points. What is the reactance between these two points, between the generator and the motor? For that what we do is we will first convert this delta connection into star connection, and star will have reactances XA, XB and XC. Then what will be XA? It will be equal to x dot x by 2 x plus x by 2 plus x by 2, that is x by 4. XB will be same, x dot x by 2 divided by 2x, that is also equal to x by 4. XC will be equal to x by 2 dot x by 2 by 2x, that is equal to x by 8. So I will write it down here. Xc is equal to x by 8. Then now how does my circuit look like? This will be my generator EMF, generator reactance. Here we will have XA, XB, motor reactance, this will be XC. These two are in series, these two are also in series. So now if we want to find such a kind of reactance, we have to convert this star connection into delta again. Let me call it as X2, that is the transfer reactance during the fault. X2 will be equal to XD double dash plus XA, XB double dash plus XM. XD double dash plus XA into XC plus XB double dash plus XM into XC divided by whole XC. This will be my transfer reactance during the fault. So here you have to determine the transfer reactance during the fault, and if you see, the fault is occurring in middle of the line. That means the reactance up to fault is X by 2, whereas reactance up to load is X. So these two values are comparable. So I cannot directly say the entire current flows into the fault. That means some current will go into the load also. Okay. That is why during the fault the power transfer will not be 0 in this case. Okay. Because the reactance up to the fault point and the reactance up to the load are having comparable values. So here we will have some transfer reactance due to which the maximum power during the fault will be mod E mod V by X2, which is also called as transient stability limit, and electrical power will be equal to P max 2 sine delta. Now during the fault power transfer is reduced very much, so it will be P max 2 will be less than P max 1. Now let us consider the case after the fault. Now since we had a system like this, to clear the fault, what we have to do is we have to open both these circuit breaker. Why both? Suppose we open this first one, then how the fault current will flow? It will flow like this. Okay. So to isolate the fault, we have to open both the circuit breakers 1 and 2. If we open this, then this line gets disconnected. So transfer reactance up to the load is XD double dash plus line reactance, that is your X. So what will be P max 3? It will be mod E mod V by X3. And if you see, X3 will be greater than X1 because XD plus X is greater than XD plus X by 2. That means P max 3 will be less than P max 1. So usually if we compare these three powers, it will get an order like this. P max 1 is greater than P max 3 is greater than P max 2. Okay. So like this, during the fault the minimum power transfer limit is present. Okay. During the fault power transfer to the load will be very low. Hence P max 1 and P max 3 are both greater than P max 2. Now let us apply equal area criteria to our case to determine the critical clearing angle. So here first we will draw a highest curve which will correspond to P max 1. The lower curve will be P max 3 and still lower will be P max 2. Okay. Now mechanical power. the mechanical power should be less than Pmax1 and Pmax3, that is, the mechanical power should be less than steady state limit, but it can be greater than transient stability limit. So this will be my PS. So initially my system will be operating at this angle delta naught, that is the intersection of PS with your Pmax1. Now as the fault is occurring, we will move from first curve to the second curve, and delta will go on increasing until the fault is cleared. Why delta is increasing? Because this is my mechanical input and this is the electrical output. Since mechanical input is greater than electrical output, so delta will go on increasing. Suppose fault is cleared at this location, delta C. Then we will go from during the fault to after the fault curve. So we will go from A to B to C to suddenly D. Then again delta will go on increasing until we reach synchronous speed. That is your delta 2. So this area here represents accelerating area and this represents decelerating area. For the critical case, what will happen is delta 2 will be equal to delta max. Now what is this delta max? If you see, it will be pi minus, let us say, theta. Where theta is intersection of PS with the second curve. Okay, this will be my delta max. Now to determine critical clearing angle, we will have to add accelerating and decelerating area and equate to 0. That is delta naught to delta max. We have to increase PS minus PE d delta and equate it to 0. So we will break it in two parts, delta naught to delta CR. What is PS? PS is PS minus electrical power is Pmax 2 plus delta CR up to delta max. PS minus electrical power is then after the fault is cleared Pmax 3 sine delta. And now we integrate the first term, we will get delta max minus delta naught minus Pmax 2 sine delta integration is minus cos delta, so I am directly putting the limit cos delta naught minus cos delta CR. Because due to minus sign, we will take lower limit minus upper limit plus PS. Sorry, this will be delta CR PS delta max minus delta CR minus Pmax 3, then again lower limit minus upper limit. Okay, so this delta CR terms gets cancelled out. So we have PS into delta max minus delta naught. So since we are trying to find delta CR, let us collect the cos delta CR terms together. So it will be Pmax 3 minus Pmax 2 cos delta CR will be equal to PM delta max minus delta naught, or PS delta max minus delta naught. PM is the mechanical input, PS is the shaft input, both are same, minus Pmax 2 cos delta naught minus or plus Pmax 3 cos delta max. From here I can calculate delta CR, that is the critical clearing angle. That is my cos inverse PM delta max minus delta naught minus Pmax 2 cos delta naught plus Pmax 3 cos delta max whole divided by whole divided by p max 3 minus p max 2. This will be a critical clearing angle. Okay, and this here is p max 2. Don't confuse it with the mechanical power. It is actually p max 2. Just due to lack of space, I have written like this. Okay, so this is how you determine the critical clearing angle. Now this is the most generic case. Even if you want to remember the expression for critical clearing angle, you can remember for this case. Why? Because from here I can derive the first case also. How? In first case, actually p max 3 was equal to p max 1 and p max 2 was 0. If we substitute here, we will get cos inverse Pm delta max minus delta naught. This term will go to 0 because p max 2 is 0, plus p max cos delta max divided by p max because p max 2 is 0. This was the formula for the first case. Okay, so that can be derived from this case also. So that is why this case is the most general type of case. You can remember this case and you can apply it for any other case as well. But here we cannot determine critical clearing time. Why? Because if you want to determine critical clearing time, what you will do is md square delta by dt square is Pa, which is equal to Pm minus Pe. But now during the fault it will be Pm minus P max 2 sine delta. So this term is not constant, hence we cannot directly integrate it. So we will not determine the critical clearing time in this case because it can only be determined by numerical solution and not directly. Next, let us consider when the fault occurs near the bus in case of a parallel line. Earlier, when fault was occurring near the bus, there was only a single transmission line, but now it is two lines. Now again, if you see, the reactance up to the fault is xg. Reactance up to the load is xg plus x. Okay, so we will again consider that entire current flows into the fault, due to which power transfer during the fault is 0. Okay, so before the fault the reactance would be xg plus x by 2. P max 1 would be mod E mod V upon xg plus x by 2. But after the fault, the reactance would become how the fault will be cleared by opening both the ends of the transmission line. It will be xg plus x. What will be P max 3? That is the maximum power after the fault. Mod E mod V by x3. This will be the power transfer after the fault. Since x3 is greater than x1, P max 3 will be less than P max 1. After the fault is cleared, power transfer capability of the system is reduced. Okay. So instead of deriving it using equal area criteria, let us derive it using the second case. Okay. So here first let me show you the power angle curve. This here is P max 1 actually. This is P max 3. Initially when we were operating at an angle delta naught. This delta naught is incorrect. This is the angle delta naught where PS intersects my first curve. Then as soon as the fault is encountered, we go from A to B. Now since PS is greater than P, the rotor will accelerate and delta will increase. At point C, our fault is cleared. We go from point C to point D. Okay. And when the fault is cleared, P becomes greater than Pm, rotor will start decelerating, and at point E, we will again attain synchronous speed. So this will be my accelerating area and this will be my decelerating area. Okay. So here we have two powers, P max 3 and P max 1. but Pmax 2 is 0. So if we directly determine delta Cr from the expression that we derived earlier, it will be Ps shaft power delta max minus delta naught. Pmax 2 term will be removed. Pmax 3 cos delta max upon Pmax 3. This will be our critical clearing angle, where delta max is actually pi minus sine inverse Pm by Pmax 3, and delta naught is sine inverse Ps by Pmax 1. So you can make it also Ps by Pmax 3. So these are the angles that we will use here. Here also, if you see, the power transfer during the fault is 0. So here also we can determine the critical clearing time. The expression will remain same. Okay, so what is the difference here? This delta Cr is different from case number 2. Okay, this is different, but the formula between TCR and delta Cr remains same, because that was derived from swing equation, and swing equation does not change for different type of fault. Swing equation will remain same. So these are the different type of fault cases that we considered. First one was the single line fault near the bus, then fault in middle of the line, then fault near the bus in case of a parallel line. Then the next reason for a large disturbance is contingency. Now suppose the system is in perfectly healthy state, but we will remove some apparatus to judge whether or not after removal of some apparatus the system remains stable. So let me say this is Xg. So initially, what is the transfer reactance? Xg plus X by 2. After the removal, what will happen? Suppose I remove this transmission line, I open this circuit breaker, reactance will be Xg plus X. So Pmax 1 will be mod E mod V by X1, and Pmax 3 will be mod E mod V by X, or let us say 2 X2. So here, since X2 is greater than X1, Pmax 2 will be less than Pmax 1. So let us see the power angle curve. Here, this is my Pmax 1, this is my Pmax 2. Earlier we were operating at point A. As soon as we remove the apparatus, delta will remain same. We will go from curve 1 to curve 2, from point A to B. Now this is my PS, this is my P. P is less than PS, so delta will increase. At point C both become equal, but delta will still go on increasing up to point D. Here again we will attain the synchronous speed omega s. Here also we have omega s. And we will equate these two areas from B to C and C to D to determine the stability of the system. That is your contingency analysis. Here we are not deriving any expression. Just I wanted to exhibit how to do the contingency analysis. There you have to take an apparatus which you will take out of the system, which will affect the affect the transfer reactance of the system to change the power output of the system. So let us summarize what we covered in this lecture. We saw fault in middle of the line. There we saw the power transfer during the fault was non-zero, and we determined the transfer reactance X2 by solving the circuit, and determined critical clearing angle cos delta naught divided by Pmax 3 minus Pmax 2. Similarly, we saw other case, fault near the bus. there cos delta CR was PS delta max minus delta naught plus P max 3 cos delta max by P max 3, and we also determined TCR, that was equal to under root 2m by pi f delta CR minus delta naught. Here delta max is equal to pi minus sine inverse Pm by P max 3, delta naught is sine inverse Pm by P max 1. Okay, so these are the two angles that we are using in these expression, that is delta max and delta naught. In the next lecture, what we will do is we will consider the case of synchronous motor and see how we do the stability analysis for the case of synchronous motor, and also we will see how to improve the transient stability.